We tend to think of AI as this abstract thing, right? Something that just exists in the cloud, totally weightless. But what if I told you its biggest problem is actually something incredibly physical? Today, we're digging into the massive energy crisis that's brewing inside the world of AI. And we're going to explore how a simple change in its fundamental shape might just be the key to a much more sustainable future.
So to really understand where AI is headed, we first have to get real about what it costs to get there. And I'm not talking about your monthly subscription fee, I'm talking about the physical costs in electricity, in water, and in carbon emissions.
This number. This is why we're having this conversation. 945 terawatt-hours. That is the International Energy Agency's official projection for how much juice data centers will be chugging annually by 2030. It's a truly mind-boggling figure, so let's try to put that into perspective.
Yeah, that is more power than the entire country of Japan, the world's fourth largest economy, by the way, uses in a whole year. This isn't some small problem on the horizon. This is a global-scale energy demand that is happening right now, and it's growing fast.
So where's all this new power coming from? Well, according to Goldman Sachs, a staggering 60% of this new demand is going to be met by burning fossil fuels. That means we could be adding over 220 million tons of CO2 into the atmosphere every single year just to power our AI.
And this isn't abstract, it has very real consequences. Coal plants in places like Kansas City, West Virginia, and Salt Lake City, they were scheduled to be retired. Now their lives have been extended by a decade, specifically to power new data centers. And in water-scarce Arizona, a single Microsoft facility is projected to use 56 million gallons of water a year. That's enough for nearly 700 families.
But let's get specific. Where is all this energy actually going? We hear all the time about the massive costs of training these big models, but that's just a one-time thing. The real energy hog, the thing that makes up 80 to 90% of AI's entire compute budget, is something called inference. That's the day-to-day work of actually answering your questions and generating content.
And the kind of model you use, well, it matters. A lot. A smaller model, like Llama 3.18b, might use around 114 joules to give you an answer. Okay. But its much larger sibling, the 405b version, it can use nearly 60 times more energy for a single query. Just think about that. Every time you ask a question, there is a very real energy cost.
But what if this isn't just a problem of needing more power plants? I mean, what if the root cause is actually a fundamental flaw in how AI even sees the world? A problem not of scale, but of, well, shape.
This quote from the research it nails the problem perfectly. AI models today, they see the world as flat. But our knowledge, human knowledge, it isn't flat at all, is it? It's this complex, branching tree of ideas and relationships, from animal to mammal to dog, all the way down to golden retriever.
And this flat geometry has a name. It's called Euclidean space. Just think back to a high school math class, grids, straight lines, simple shapes. It's super easy for computers to work with, which is why we use it. But it turns out it has this massive, hidden cost when you're trying to represent complex information.
Okay, so here's the core mismatch. The complexity of knowledge, it grows exponentially, like the zillions of branches on a tree. But the space inside that flat Euclidean world, it only grows polynomially. It's like trying to cram a giant sprawling oak tree into a tiny cardboard box. It just doesn't fit. So to make it work, you have to add hundreds and hundreds and hundreds of dimensions, which is exactly why these models are so gigantic and so incredibly energy hungry.
All right, so if flat geometry is the problem, is there a better way? Well, this research proposes a totally different kind of geometry, one that actually has the same natural shape as the information it's trying to represent. It's called hyperbolic space. And instead of being flat, it's negatively curved, kind of like a saddle. In this strange space, the amount of room, the volume, it expands exponentially as you move away from the center. It perfectly matches the tree-like structure of our knowledge. It's a geometry that's basically purpose-built for how we organize information.
And the potential payoff here? It is enormous. Just by switching from a flat geometry to this curved one, researchers have been able to achieve a compression factor of 24 times. That means we can represent the same amount of information in a tiny fraction of the space.
So what does that actually look like? It means taking this massive 768 number representation of a piece of text, they call it a vector, and shrinking it all the way down to just 32 numbers.
And here's the kicker. You keep over 97% of its original meaning. I mean, this isn't just a small tweak. It's a radical reduction in size.
And this is exactly where that abstract idea of geometry crashes right into the physical world of energy consumption. This whole idea isn't about building bigger data centers. It's about building smarter, more efficient representations of data.
Now here is the absolute key to understanding the energy savings. Inside a modern computer chip, the biggest energy cost isn't doing the math. No, it's physically moving the data around, shuttling it from the slow, power-hungry main memory over to the super-fast cache that sits right next to the processor.
Think of it like this. Using that standard 768 number vector is like sending a 768-page document every single time someone asks a question. But the 32 number version, that's like sending a concise 32-page summary instead. You are physically moving 24 times less data every single query.
And this kicks off a whole cascade of savings. That smaller 32-number piece of data, it fits right into the chip's fast, low-power cache. That means you avoid constantly having to go get data from the slow, energy-guzzling main memory. Less data movement and less computation means less electricity used, which generates less heat, which in turn requires less energy and less water for cooling. It's a chain reaction of efficiency. And you have to remember, the process of creating this super compressed model is a one-time cost. It happens once, but the energy savings? Oh, those apply to every single one of the billions, maybe even trillions, of questions that will be asked over the model's entire lifetime.
Okay, now this all sounds incredibly promising, I know. But like with any major scientific shift, it's really important that we stay data-driven and be honest about the challenges.
So, we have to ask the critical question. Is this whole geometric compression thing a silver bullet? Well, the short answer is, it's a little more complicated than that.
See, there's a trade-off here. On the one hand, a 24 times data reduction is a massive win for energy spent moving data around. But the math involved in this hyperbolic space is actually a little more complex for a chip to perform than simple Euclidean math. The big bet is that the huge savings from moving 24 times less data will more than make up for the tiny extra cost of doing slightly harder math. But the ultimate net savings? That's going to depend on the specific hardware, and it absolutely requires dedicated benchmarks to prove it all works at a massive scale.
You know, this research really forces us to ask a profound question. Can we build an AI that isn't just more powerful, but is geometrically wiser? An intelligence that doesn't just understand the content of our world, but also understands its inherent shape. It's something to think about.